Hello, wonderful people of the internet. Welcome back to another episode of Rambleleos. Today, we're just going to ramble about stuff while we pretend to do programming. And I just realized I'm in the wrong chat here. So let me just close this and pull up a new one, just in case people were actually chatting. Sorry about that. Bring this down over here. Perfect. Anyway, guys, I hope you're all having a great day. Let me see who was actually in chat. I don't know if there was anyone there. That's okay. But yeah, so today we will be continuing the work that we were doing last week on the fractal flame method. So that's what we'll be doing today. Lucas, hey, how are you? I hope you're having a great day. And anyone who might be lurking in chat, hey, thanks for being here. So for those of you guys who were not here for the last stream where we did fractal flame methods, essentially, let me go ahead and pull up the image that we generated. CD projects, Flameify was what it was called. L is here. And now let me open up, what was it called? Probably save something.png. So let's just do Mirage. Save 2.png, sure, doesn't really matter. We made a bunch of images that look something like this. So we have, and I'll explain what these are in just a second, but essentially what we were trying to do, you know, looking at this now, it doesn't look nearly as bad as I thought I did last time. Actually, I think it looks probably fine. So anyway, last time we made a bunch of images that looked like this. And today we're going to kind of keep working on this, make better animations and kind of better fractal flames and stuff like that. So what is it exactly that we're looking at? That's a very good question. Thank you so much for asking. Let me see. Where am I going to put? Where did I put this? Videos, algorithm archive, iterated function systems, LS here. What you just saw there was actually a combination of a bunch of different functions, all of which act on or act with something known as a chaos game. The easiest way to describe this is by talking first about iterated function systems, and I'm going to show that to you right about now. So if we do MPV, sierpinski Hutchinson.mp4, and we play this, essentially I'm going to show you how to create a Sierpinski triangle with an iterated function system. The idea is that if you have 3 points, A, B, and C, you can then create 3 functions for each point, or one function for each point. So the idea is function 1 will bring your point halfway towards A, function 2 will bring your point halfway towards B, and function 3 will bring your point halfway towards C. If A, B, and C all have children, D, E, and F, and then these children have children, you know, one set of children will move towards A, another set of children will move towards B, and another set of children will move towards C. As they generate more children, and those children generate more children, and those generate more children, and more children, and more children, eventually you create the Sierpinski triangle. Now, this is created by iterating through an entire function system, right? So you have a whole bunch of functions that are all working together in order to create this shape. Now, when we were looking at the visualizations we just had a second ago, that was actually a combination of multiple different function systems put together. So not just something like the Sierpinski triangle, but also something that maybe rotates, and something that creates a heart shape, and something that creates, you know, all of this other stuff. And so we've got a lot of work to do to finish up the fractal flame method and have something that looks really, really eye-catching and beautiful. But I think we are kind of getting there one step at a time. So CD back into projects Flameify. And I'm actually going to have that image that we just generated up in the upper left-hand corner, just so we have something to look at and something to compare our subsequent images to. So also, let me open up a new terminal. Projects Flameify, Mirage, save, sure, 1.png. Sure, that'll be it. And we'll just leave this up here or something like that. And maybe move it over here or something. I don't know. Just kind of moving it around a bit. We got to move this down. Something like that should be fine. And I'll just have this under there. Okay, perfect. So now we have everything set up. Again, this is the image that we have up here. You can see the heart in pink over here. And last time we generated an image, this was the last image that we generated, which should be a combination of a bunch of different things, in particular, a bunch of different functions, log scale plotting, and all of this kind of stuff. So that's where we're at. Let me get a quick sip of water, and then we can go ahead and hop into it. The next thing I'm going to do is actually pull up the paper for this particular method, which is available here. Let me just Google it so everyone can get it in chat. 1 second. So let's do fractal flame method. Sure, that'll do. And let's do high performance iterated function system. This one, that's the paper. I'll give you guys all a link. And yeah, if you guys have any comments, questions, concerns, ideas, anything like that, just let me know, and I'll totally address it as soon as I see it in chat. So what am I doing? I'm going to go ahead and open up Julia. So we have it available. And I think what I'm going to do is I'm going to open up the code that we have. Well, no, I'm going to open up the paper first, and we're going to go through what we have. and then see what's left to do. So we're going to cd into projects. This L is here. I guess I'll open up in Zernal. It doesn't really matter too much. Zernal is just easier to take notes with. And we'll do flame draves.pdf. I'm recognizing that chat is a little bit quiet today. So again, if there's anything that you guys want to say in particular, just feel free to speak up. And we'll just see how this goes. I've actually been noticing that pretty much throughout the Fractal Flame session, we haven't been having too many views. Not that that really matters, like it really doesn't matter, but you know, it's an indication of how these videos will do on YouTube, and that's the main thing. So what have we done with this paper so far? So we've talked about classic iterated function systems, and in fact, let me move this over here so we at least have the image up as well. So we talked about classic iterated function systems, which is fine. Then we had, let's see, variations on the iterated function systems. Again, we just had a set of swirl, heart, and stuff like that, horseshoe, but we'll add more variations later. We have the post and final transformations, which we have to update later, but we already did log scale density, coloring, and gamma correction. So now we have to do a few additional things for symmetry, filtering, motion blur, directional motion blur, and other things as well. So we still have a lot left. I'm pretty sure symmetry will take us all afternoon or evening or whatever. So we'll just see how it goes. Right now, I'm just watching. This is a little over my head, just interested. Yeah, I do realize that. Like, I've been realizing that more and more, that pretty much the content that I make is, like I was talking about this the other day, even on stream. Hey, Alexor, how are you? The content that I'm making isn't particularly approachable, although there are some people in chat that really do like go the extra mile. Like, for example, Psycode on Discord. If you guys aren't on Discord, go there right now, if you can. Recently put up a video that was precisely the Fractal Flame method, but like completed. And this does happen a lot. Like, you're in the middle of implementing something, and then you know, people in chat, you know, they're able to take it to the next step, and they're actually able to finish stuff that I was not fully able to do myself. So anyway, I think that's what we're gonna do. We're just gonna try to get the symmetry section done today, and I think, yeah, we'll just see what happens. We need to think about how we're going to implement this function. And in fact, let me go ahead and open up the file as well to see what we have left to do. So let's go into ls here, vi source, and then fractal flame.jl. Right, so I've got a few things that I want to do here. Set the affine transformation for every flame. So this way you have basically a set of affine transformations and a set of flames to apply. So I guess, I need to think about how I want to do that exactly, but it's not particularly hard to do. So set affine transform for every flame, and here I'm just going to say 2 vectors. 1 second. 2 vectors. 1 for functions. The 2 for affine. Sure, that'll do. I'll remember what that means. Okay. And then also we have to do the final transform, which we have not done, but you know, we can set the final transform. In fact, let's just go ahead and do that right now. Let's take a look at all the different functions here, implement a new fractal function, and just kind of get something working here. So which one do we want to try here? We have sinusoidal. Sinusoidal looks kind of cool. How about we do sinusoidal? That one looks nice. So we're going to go into right and quit here, vi source, and then I'm going to go into flames.jl, and we're going to create a new function here, function sinusoidal. I'm just going to take p point end here, and then we're just going to implement it. So we're going to say return. I think we can just return, can't we? We'll see. Point. And then we put in the x coordinate, which is going to be sine of p.x. And then the y coordinate, which is cosine. Oh, no, it's also sine of p.y. And then I think the last one is just point.color. Oh, in fact, I think it's just black and white right now. So I think we can just do that. Now, what we do need to do is provide a color for this. So let me see. Polar down here should actually be polar color. That was something that I missed before. Red, green, blue. So that might cause an issue. So in here we're gonna have a sinusoidal color associated with this. So I guess it's gonna be there. And I guess we're going to do red, green, maybe. Are we using green? Maybe. I don't know. So let's just do green for this one. Sure. And it's going to be called sinusoidal color. Sinusoidal color. Said color twice. Okay, perfect. Fractal Now let's go down here and implement the final transform. So we're going to say final f is going to be equal to sinusoid. Hey, Marco Dev, how are you? That should work okay. Oh, sinusoidal. And then after that, we are going to do more on water. I guess that's just because I always say I'm going to get a quick sip of water or something like that. So we have the final f here. And then that's not actually what we're doing. The today command, I don't, like, again, I didn't code Botuleo, so I'm not exactly sure what it's trying to say at any given point in time. So now we're going to say, I think all we want to do is we have the final function, and now we're just going to say for I is equal to, I think I'm just going to go through all points, 1 to n, and then end here. In fact, I can probably just put it in that loop above. So let's do dd here, paste in here. And then down here, we're going to say points. I think I want to make it so it goes through all points here. So 1 to n, and then say if I is greater than 2, 2, we do the following. Greater than 1, sorry. Was that 5 spaces? 1, 2, 3, 4. No, that was right. If I is greater than 1, and then we apply the final function so points of I is equal to final function of points of I. Okay, and that should do it, I think. So let's just see what happens if we go over here, open up the Julia REPL, and we just do using revise, and then using flamify just to make sure it all works. And then after that, we should be good to go. The very next thing I'm going to do is actually make it so all of these functions, we have like a color set associated with the function set so that, yeah, so it works slightly differently. So now I'm just going to do using flamify. Oh, did I forget to do, I forgot to do something, 1 second. Julia _ project. Okay, now let's do using revise. And then using flamify, and it should work okay. So now using flamify, come on. Am I in the wrong directory? I am. CD projects, flamify. All right, let's do it one more time. Julia _ project. Now we're going to do using revise. Oh my gosh. Oh, I'm not doing well today. It's a day. Using flamify. There we go. Now we have it available. This should compile without too much trouble. There we go. And then we're just going to run it just to make sure it works. And then we're going to start modifying the code just a little bit here and there. So let's do the last flamify dot flame. I believe this is okay. Let's just see what happens if we run it. I don't know. Might take a minute. So let's go here and let's create something called a color set. Okay. And in here it's going to be equal to, let's do RGB. And what do we want here? For swirl, it's going to be 0, 0, 1, red, green, blue. For polar, we're going to make it RGB of, oh, I'm not really sure here. RGB, what do we want for polar? I think polar should be blue, so swirl should be green. So this will be 0, 1, 0, 0, 1. For the heart, it has to be pink, obviously. So RGB of 1, 0, 1. And then horseshoe, I guess we'll just make red. Okay, so what I did here is I created basically a set of colors. I'm also going to have a final color. It's going to be equal to, I guess the only color we have left, which is going to be RGB, RGB of 1, 0, 0. So this is, we have green. Oh, we don't have red. No, we don't have this color. Red, green. The mixture of red and green is ugly though. So maybe, let's see. So we have blue. We have green, blue, pink, and red. But we don't have green and blue mixed together. That'll look good. Okay, so now we have the final colors. So we're going to say this is equal to that, and then I think I want to mix the colors afterwards. Let's take a look at what the image looks like. So let's do mirage, check.png. Huh. That is very interesting. Wasn't exactly what I was looking for, but it does look cool. I have to admit, I think it looks pretty good. It just looks really weird. Okay, so we're going to keep working on this and making it look pretty good. It'd be interesting if we had a scientific computing language that would be called Shakespeare. There's already a language called Shakespeare, as well as Hamlet. Haml. However, another one is here is programming language. As we can say, R is Romeo, and Juliet is a nice JIT language. That's fair. I think it's green, because I'm not properly mixing the colors. So here what I'm saying is that all of the points, so the points color should be a mix of, yeah, so I'm not properly mixing the color. So let's go here. And what I want to do is final F. So what am I going to do here? I'm going to say, give me a second. I need to think about this. So we have the points I, and then we're going to say the points I dot color is going to be equal to, let's do color set of, I guess it's going to be, okay, let's do rand between 1 and length of function set. All right, and down here we're going to do f is equal to, no, okay, so let's say chosen is going to be equal to rand here. And then we're going to say f is going to be f set of chosen. All right, and now we're going to say color is going to be color set of chosen. Sure, that'll do, I think. And then down here we want to mix the color. So here we're going to say points of I dot C is going to be equal to mix color. What is it called? I think it's just mix color of 2 different colors, but we'll see. Rank here, go into VI, source and image tools, and his mix color, it takes a pixel and a point. But I think actually I want to create a new function for mix color, which takes in 2 colors. So it takes in, I guess A, which is going to be of type RGB, and B, which is going to be of type RGB. And then it's just going to return the average of the 2. So it's going to return, 1 second. It's just going to return RGB of A dot R plus B dot R over 2. And let's make sure that works. And then it's going to be A dot RGB G plus B dot G, again over 2. I should probably multiply it by 0.5. Let's do it that way. Sure, that'll do. And then 0.5 here. Okay, and then finally we do blue, RGB. I'm very bad today. 0.5 times A dot B, and then plus B dot B. All right, wonderful naming conventions aside, I think that'll do for mixed color of 2 different colors. Rank put here, fractal flame, and now we're just going to do mixed color of, I guess we don't even have to mix the color here. We can just say points color dot, points of I dot C is going to be mixed color of, and here we're going to say, okay, never mind. I think I did need that. So in here, we're going to say the points of I is equal to that. So we're going to say points of I dot C is going to be equal to color set of chosen. Put that in there again. And then in here, we're going to say points of I dot C, and then the next thing we need is the final color. Something like that should do. Okay, now I think this is going to break because I think points, I don't think we're allowed to do this call right here, points of I.C, because I think points is mutable. Let's try running this and just see what happens. Because I don't think point, the struct point, is mutable, so I think that's going to break. Yep, so set field immutable struct of type point cannot be changed. Now we can do two things here. One, we could just make point mutable, which is what I would probably do in this case because it's kind of a pain. I mean, we can also change this to make it so this is now points of I is going to be equal to points of I, point of points of I dot X, and then points of I dot Y, and then color function. Like, that'll do. Like, this will work. Points of I is going to be equal to point of points of I dot X, points of I dot Y, mix color, and let's just run that. So that should work. It's not gonna look quite as green as the last one. So we'll just see what it looks like when it comes out. What is this abomination? Smart doing it the functional way. Yeah, so the issue was that, let's take a look, mirror check.png. Okay, so now it's blue-green, which wasn't exactly what it's the same color. Interesting. So our colors aren't blending correctly is what I'm betting here. What is this abomination? Yeah, so the issue is that all the types are immutable by default. So I just, we can't change the contents of the point. So the point locations are all where I expect them to be. The point colors are not what I expect them to be. And the reason for that is that, let's see, we have the color set of RGB. Why are they all just teal? It's probably because mix color isn't working correctly. Let me see what happens if we open up the mix color function again. So we have RGB of A.R plus B.R times 0.5. Let me just see what's happening here. I mean, clearly all the colors are coming out teal, right? Yeah, we're in the debugging phase. So let's just print line. There we go. I forgot the Julia print statement. Print line of points of I, one second, I dot C, and see what we get. So here we're going to do, that's a lot of points, so let's just do 1,000. They are all RGB floats 0, 0, 0. Wait, what? 0, 0, 0.5. 0.5. Oh, I see. It's just, okay, so it's half green, half blue. And the reason for that is that, all of the point colors are black for some reason. And that is because, I don't know. Color set of chosen. So we have, okay, so let's do this twice then. We're going to yank and paste this up here as well. And let's run that. Okay, so here we have, oh no, that's not true at all. It's 0, 0, 0, 0, 0, 0, 0, 0, 1. For some reason changes to 0, 0.5, 0.5. So for some reason it's all turning, yeah, it's all turning some sort of greenish blue. I'm not exactly sure why that's happening. So let's, I guess, just keep, so the mix color function must be, what is the mix color function doing? It's taking in, it's points of I, what is it, huge number? This huge number here is just 0.4, it's just floating point precision. So it's not a big deal. Okay, yeah, it's roughly 0.5. Okay, so why is it's basically reading in blacks. So instead of, so it's supposed to be reading in red, green, blue. So it's supposed to be blue mixed with teal, but for some reason it's just mixing blue with, or it's mixing black with teal. Like all the points.c colors is that. So let's go ahead and yank this and paste it up here as well. Okay, and now let's do Flameify. Okay, that's not what I expected. Wait, what? Wait a minute, what do we have here? Red points of I dot C. Before and after should change. But in here, if I is greater than 1... Oh, wait a minute. I see what I'm doing wrong. I'm what you might call really stupid. Yeah, I totally understand now. Gotcha. I gotcha. VI source flames. Because now the colors are not created in the flames themselves. They're created outside. We no longer need a sinusoidal color, and so we can remove all the colors defined here. So color here. So let's do DT there, I guess. And we're just going to remove all the colors. So all the points when they come out of these functions are going to be black. There, let's just do that for all the functions. This way we don't have to deal with the colors at this scope. And I think that's for the best, honestly. DD. All right, keep going. Keep going. Ah, for Pete's sake. Why? All right, there, DD there. And then finally, this one doesn't have a color associated. So anytime we have color, I'm just going to delete that line. Okay, so now there's no colors defined on this scope. So now we're going to go into source fractal flame here. And so we define the final color there, right? So what I'm going to do then is I'm going to say transform color here. This is going to be annoying, but this is just what I'm going to do. It's going to be equal to this here. All right. And that should work just fine. Now we're going to DD there, DD there, DD there, and change this to transformed color. And that, I think, should do it. Okay, let's see what happens if we run this. And then we take a look at the image. Wow, look at that. Look at that beautiful image. We're going to have to try that again with way more points. So let's just increase it by 100. Check.png. There we go. That looks a lot better, right? I mean, clearly it's not as pretty as the other one, but that's because every single color in the image is being combined with teal. So increase it again by a factor of 100, and let's just see what happens. I can't see the difference between a comma and a period with this font. Sorry. It's random pretty much, regex and Perl, some set awk. Again, I could change font, but I quite like this font, so I don't want to change it. Let me get some water. Okay, I didn't realize this would take so long, or else I wouldn't have run it. But yeah, we'll just give it a second to finish outputting something, and we'll see what it looks like. And I think that will be it for the color manipulation here. And the next thing we want to move on to is dealing with symmetry and stuff. So that's the next bit of the paper that we want to work on. So again, we're gonna have a before picture, which is this one in here. In fact, am I doing the log scale? Let me see. Maybe I'm not. Let's go into VI image, source image tools. Am I doing log scale? 2RGB, right image. I think that was down here. 1 second. Where was the log scale stuff? Mixed color, 2RGB. Here's the log scale. So yes, this is with the log scale associated with it. Right. Okay, there's a lot of to-dos left, but it seems to be kind of okay. So maybe it's fine. Is it done yet? No, it's not. Okay, so I guess while it's running, we will go ahead and start reading up about symmetry and stuff like that. I meant when you're moving color functions, you could use regex and VI. Oh, right, I definitely could. But I didn't because I'm what you might call a noob. Okay, so I'm gonna scroll up a bit. And I think we're ready to go ahead and start attacking symmetry. So again, guys, if you have any comments, questions, concerns, or anything like that at this point, feel free to let me know. I think what I'm going to do is I'm going to I'm going to go ahead and commit what we have, just so, well, once we get the image, I'm going to commit what I have, and then we're going to start attacking symmetry, because I think symmetry is actually going to get a little bit complicated. Also, today might be a little bit of a shorter stream. It might not be a full 2-hour stream. I'm feeling really tired today. I've been feeling really tired recently for just, I don't know why. I've just been really tired and just burnt out and all that kind of stuff. So obviously I'm still streaming. I'm still making progress. But if you noticed, I didn't stream over the weekend. This wasn't, I've been kind of in my mind. I've been wanting to do longer streams on the weekend. But I just haven't, because it's a bit about time, but it's more about time management, right? Like, I've been running into a situation where, like, you know, I could be spending X amount of time streaming, or I could be spending X amount of time working on things related to new YouTube videos, or like learning things that we can use later, maybe doing some writing on the side, because I do need some sort of creative outlet and stuff like that. So, I don't know. It's been, I'm sorry that I've been kind of out of it recently, but the other thing too is, again, the Fractal Flame series hasn't been getting too many views on Twitch, so I haven't felt like, I don't know how to put this. Like, I know this sounds really mean, but like, I haven't felt like it's a huge opportunity cost to not do the stream. You know what I mean? And I know that's a really slippery slope to go down and everything. Man, this is taking forever to calculate this Fractal Flame. So we're just going to read the next section, and then we're going to go from there. Also, I added a new screen. It's called the Ramboleo stream. So now anytime, or Ramboleo screen. So anytime I'm off topic, I intend to put this screen up so people know that I'm not saying anything of any importance, and they can probably tune out if they need to. Anyway, let's get back to reading about symmetry. Okay, so I'm just going to start reading, and whenever the image is done, the image is done. Okay, so the human mind responds to symmetric designs at a fundamental level. When the matrix coefficients are chosen at random, the chances of symmetric design appearing are vanishingly small. Now, what matrix coefficients are they talking about here? Are they talking about the matrix coefficients for the affine transformations? That is a good question. So what matrix coefficients are these for affine transformations? I don't know. The chances of symmetric design appearing are vanishingly small. We can easily inject such functions intentionally, however. The result appears in figure 5. Okay, so here's the image. I think, as an image, that looks pretty cool. Like, look, it's not the same as the other image that we had, but this looks really cool. It looks like an eyeball. Like, that's pretty cool. I'm a big fan of that one. Yeah, I'm actually a big fan of this one. I think we actually got this. I think this is exactly what we wanted to see. All right, I'm a fan. Let's go. So let's see. I think I can just go up here. So that's the image we just generated. Man, that one looks really cool. I'm a fan. Like that's just neat. Okay. So let's just keep going here. So I think that there's some level of randomness that we're not injecting into the system that we should inject into the system. And I think that has to do with the affine transformations. So we need to think about how we're going to do that. I've already got an affine function. So maybe it's a matter of just like setting, you know, creating a set of random matrices. So I'm going to try one more thing here. So what I'm going to do is I'm going to cp check.png into save, let's use save4.png. Okay. Just to make sure we have it. And now I'm actually going to, let's just minimize that for now, and let's mess around with the affine transformations. So I should have an affine function. L is here, L is source, and it should be in VI, I'm going to say transformation, source transformations.jl. It's literally just affine. It's just multiply an array by, I'm sorry about that, Delphi. So we have affine a times p.x.p.y1. So we checked this before, we know it works. So let's go into VI source fractal flame, and now let's go ahead and create our affine set in here. And we're also going to create a final affine, or okay. So now I'm going to create a function to create these guys in here. Let me go here. Oh, Lana Lux, how are you? Thank you so much for rating. How was your stream, by the way? So if you guys are here and you haven't been to Lana's stream before, check her stream out. She's really cool. She's a game designer. She always has like really cool games that she's looking at. I tend to like just lurk in the stream whenever I'm just kind of, you know, maybe lacking motivation a bit and you just need to focus and get work done, you know? She's a really cool streamer, and I definitely recommend checking her out. So for those of you guys who may just be coming in, hello, I'm Dr. James Schloss. Equals something. We're gonna put this in there in just a second. Just let me just pop this down here, and then we'll talk about what we're actually doing here. Right. So what are we doing today? Today we are making pretty pictures. So this here is a picture we just generated. Looks a bit like an eyeball. We generated an image like this before. We generated an image. These are all the images that we've generated so far. I'm gonna talk to you about what these images are, why they're exciting, all this kind of stuff right now, and then hopefully you guys can join and just hang out, chat, you know, whatever you want to say. If you guys have any questions, comments, concerns, feel free to let me know, and we'll go from there. So what are we implementing today? It's called the fractal flame method. So let's go over here, and I guess I have a video somewhere. CD videos. Let's do videos. Probably algorithm archive, iterated function systems, LS here, MPV. Probably this one. Right, okay, so I'm going to show you guys exactly what the underbelly of this method is, and yeah, go from there. So the way this method works is through something called an iterated function system. Now, an iterated function system is a set of functions that you iterate through. So, for example, let's say we have 3 points, A, B, and C, and 3 new points, D, E, and F, okay? Now let's say we have a set of 3 functions. One function will bring you halfway towards A, another function will bring you halfway towards B, and the third function will bring you halfway towards C. If D, E, and F all generate children, then we'll have one of their children move along one of the functions. So 3 kids will move towards A, B, and C, and we'll have this kind of weird set of triangles, right? Now, if all those kids generate more kids, you'll create more children like this. And if they generate more kids and more kids and more kids and more kids and more kids again, eventually you end up with this Sierpinski triangle structure. And again, it doesn't matter how you iterate through the function system. This set of functions, one that will bring you half towards A, half towards B, and half towards C, will always generate a Sierpinski triangle, right? And so this is this type of order, even though you're just kind of randomly ambling about this weird two-dimensional space. So what we're looking at in these images over here is actually a set of different function systems all put together. So the idea is not only, it's like we have a rotational or like a heart-shaped swirl. So for example, here you can see that we have like this weird heart shape being formed. And if we go over here, you can really see it. So here you see we have this pink heart in here. So one of our functions will generate a heart. And you see it's kind of printed here as well, right? Another one will rotate said heart. Another one will create a swirl effect on the entire image, right? And then another one can do like this sinusoidal pattern. So it's kind of lower density in the middle and higher density on the outside. And when you put it all together, you can create a whole bunch of pretty pictures. So that's how we're at. I didn't ignore the raid. I do apologize that you guys think I did, but I promise you I didn't. Alchemunch, I can't pronounce that name. I'm so sorry. Tesselhoff, thank you guys so much for following. I really appreciate it. Also, like, when you say that, this is going to totally ignore the rate of 180 people. Like, I'm like, what do you think I was just doing? Like, just for the record, like, if I ignored the raid, I wouldn't have gone through and explained what we're doing. I don't know. Anyway, it's fine. So let's see, what do we have here? Lana, wow, looks pretty... Lana's the best game. Yeah, she's really cool. I'm a big fan of Lana's stuff. Definitely check her out if you haven't already. Give me my discrete mathematics vibes. I wish I saw the stream before taking the class. Honestly, we are doing a lot of math here. That's what we do. You followed those tutorials really well. Not easy. I couldn't keep up. Have a tasty meal. Okay, so I don't think Lana appeared in chat. Oh, there she is. Hey, sorry for grabbing something to eat. Thank you for the kind intro and explanation on what you're doing. Yeah, so Lana, obviously, thank you so much for coming in. Big fan of your stuff. And yeah, of course, if anyone has any questions, comments, concerns, feel free to let me know. I'm going to catch up on chat, and then we're going to get back to the programming here. Also, Lime Die, thank you so much for rating with a party of 2, and Shift 256, thank you so much for the follow. Really appreciate it. Let's see, what do we have here? Racing Mars, thank you. I'm trying to catch up on chat before it goes above my screen. Giving me discrete mathematics. You follow these tutorials really well. Am I allowed to share something I made in Blender in chat? Yeah, please do. Generating children. Well, okay, it's not generating children in that sense. It's like each point has an additional kid. Let's see. What do you mean he's ignoring the raid? He's explaining to us what he's doing. He's bringing us up to speed. Give him a minute. Alien mathematic, top secret technologies. I'm hoping that this stream doesn't come across as too mathematically foreign. Like, I'm trying to make it very approachable. So if I'm failing in that regard, let me know and it just tell me that didn't make sense, or you said something in a dumb way or something like that, you know? I appreciate like any criticism and any comments and anything like that. Let's see, super impressive code, write a review. Yeah, so we're still kind of messing around with the code. We're very far from it being done. What's the language right side of your screen? That is Julia, the programming language. What OS are you coding on? This is Arch Linux, by the way. Let's see, what language here? I think if you just go here, and wait, chotomate, here, and you just do OS, I think it will tell you my operating system. There we go, perfect. Can I post a room render I made in Blender? Yeah, I said you could. Maybe no problem. Let me see what we have on Twitter over here. There's my Twitch stream. And let's see. This is pretty good. You said for your first week in Blender? That's actually really good. I mean, you have the Spring thing over here. If you guys don't know, Spring was a one of the Blender movies. So Blender periodically will produce movies that they show to people. It's pretty cool. And so I think this is really good for a first week in Blender, honestly. First I've seen Julia on stream, I recall. Yeah, so I tend to use Julia just because I know it. It doesn't mean it's the best language for everything. Okay, so I do think that I am all the way caught up. So now let's catch you up on the last bit of stuff that we did. So the way this particular method works is you generate a random point. And this random point will choose a random function, right? And then that random function will have a random color associated with it. And then on top of that, you have a transformation that you apply before applying that function. So we have the function and we have the color, but we don't have that random transformation beforehand. So what I need to do is I need to create basically that random function to transform the point's location before applying the function to it. The more I think about it, the more I wonder if this is actually what I'm supposed to do. So let me actually open up the paper that we have here, and let's read in a little bit more about this affine transformation. After that, we need to talk about symmetry and stuff like that. There's actually a lot to do here. Let me get a little bit more water. Chowky, thank you so much for following. Really appreciate it. And again, guys, I do appreciate any comments, questions, concerns you have. Again, it tends to be a bit chill when we're doing Fractal Flame stuff, so I'm doing the best I can to make it as approachable and friendly as I can. But, you know, it is what it is. I seriously think Julia will replace Python. I loved your super quick explanation. It roughly sounds like L systems. Is there any overlap? I don't know L systems, so I can't tell you. I'm so sorry. It's sad you can't fast forward on mobile because the delay gets longer and longer during pauses. Right. So you should have quality options at the very least. Oh, I don't have quality options today. I'm so sorry. Let me fix that really quick. I didn't realize I didn't have quality options today. That happens periodically. So let me drop my bitrate down to 2000 for those who have bad internet. And we should be back up now. So I just dropped the bitrate, and it should be okay. So I'll keep watching and learn. Okay. So hopefully a 2000 bitrate shouldn't be too annoying for people watching the stream. I realize that's like, you know, embarrassingly low for video game streamers, but for me doing stream like this, I think it's fine. Do I choose 1080 source? I think, right, so I think I usually do have quality options, but today I don't think I do. I think I only have 1080. So, follow-on question, are you a Blender user? Many uses? Yeah, I use Blender. So if you go to my YouTube channel, here, you can find actually quite a few videos that I've done in Blender. So let me just go here, paste this over here. So my most popular video, most popular, here. So this one's done in Blender, this one's done in Blender, this one's done in Blender. There's a few others done in Blender. Gaussian elimination is done in Blender. So I use it quite a lot. You should lower this to 30 FPS so the bitrate cut isn't that visible. I don't know if I can do that, but let me check. Because I don't think I can change that aspect of the stream while I'm streaming. Sorry about that. So there isn't really much I can't change the output frames per second while I'm streaming. So This is actually the first stream in a very long time I haven't had quality options. So that's why I was quite taken aback by it. Watch stream at 4K, 144 FPS. That's not going to work. You're lower 30 FPS. Nice. Wow, these are impressive results. Yeah, I think it's pretty cool. Okay, so what I need to figure out now is when we need to do that affine transformation, right? So essentially there's a transformation we have to apply before every function, right? And after every function. So what I'm trying to figure out now is how, if there's just like an affine transformation applied every time you do a function. Let me just see what we have here. So let me just, I can't quite search because of the way I have this pulled up. But let's see, what do we have here? So we now generalize this algorithm. The first step is to use a larger class of functions than just affine functions. Start by composing a nonlinear function vj from r squared to r squared with the affine functions. Okay, so I'm not sure if we have to actually apply an affine transformation. Oh, sorry about that. Here, let me go ahead and give you guys a link there. So there's this document as well. I'm not actually sure if we have to apply a separate affine transformation or if the function itself is the affine transformation. Can you explain what sorcery you speak of? Right, so just for those who might not know, let's open up Zernal PP. Okay, so there's okay, so let's say we have a function, right? So we have a point in space, and this function will, I don't know, so let's say this is the origin of the map. So here's the center of 0, 0. And we have a point here at, I don't know what that's going to be, but we're just going to say it's 1 in x and then 4 in y or something like that. So if we apply a function to it, let's say a rotational function, it'll rotate something like this, right? Which is great. My question is, when we apply this rotational function, is there another transformation we have to do on top of this rotational function? Or is it just rotation? Right? Because the rotation function we know, it's basically just a sine and a cosine. But the question of, do we apply an additional transformation on top of it? Like maybe an additional rotation or an additional transformation? That's what I don't know. Alex Tengu, thank you so much for following. Really appreciate it. So we're just going to try something, like just completely at random. So let's just go ahead and not discard that. Cancel. Move this over here just so we have it. And let's just mess around, see what we can do. So the first thing I'm going to do is write and quit vi source and then transforms. I'm actually going to create a random function. So function, I think I can just do base.rand, overload that function. And this is going to take, I guess it's, no, let's just do affine random. Okay. And this is just going to, you know what? It's just going to take in, it's just not going to take in any arguments. We're just going to end here. And it's literally just going to return a random affine transformation, which is just going to be rand. I think I can do it this way. Rand. Do I need a translation as well? I feel like I do. Rand here. And then there, rand. And then finally 0, 0, 0, 0, 1. And I think that'll do it. Okay, so now we're going to write and quit. Go into Fractal Flame, go in here. And essentially our affine set, the set of transformations we apply to every function, is just going to be a different set of affine rand. And then I think we can just paste that a couple times. So let's just paste it a couple times and see what this does. I have no idea. Okay. And then finally, our final affine transformation will be this one. There. So now I think what I have to do is apply the affine transformation to a point. So let's take a look at our transformations again. And I have affine, which returns a point, location, color. Should be okay. So let's go in here. And now what we're going to do is we're going to say points of I. And then finally, let's see, that already sets the color. So I think I actually want to do it this way. Points of I is going to be equal to affine, and I think it's points of I first, and then I think it's going to be the affine set of the chosen value. Let me check to make sure that's right. Oh no, it was the affine array first. That is okay. And then we're going to do the same thing down there. Points of I. Okay, so then down here we have the transform color, and we're going to do yank paste, and we're just going to do affine d $, final affine. This might look absolutely awful when it's done. I have no idea. Points of I. Okay, let me add some spacing just to kind of make this a bit cleaner. Okay, and now let's just run it one more time with a few fewer points. This will take a few seconds to run. I have no idea how long. Space Kepler and also Alex Tengu. Thank you guys so much for following. Sorry if I missed that a bit ago. Could you make a function which duplicates an object in a random direction with the same distance between the next? Could you maybe re-ask that question, because I don't know if I fully understand it. Sorry about that. Could you make a function which duplicates an object in a random direction? So you like take a point and it just sends it scatters, essentially is what you're saying. Doing geographic information systems? Not that I'm aware of, but maybe to get cool designs. All right, let's just see what happens when this outputs. It takes a bit to render because I'm not really parallelized. Honestly, iterated function systems are inherently iterative, so they're not very good to parallelize. Perhaps the dot in the middle expands? Maybe. Check.png? Oh no. Well, that didn't work out, did it? We went from like really cool designs and stuff to that. Ah, darn. Okay, so what does that mean? Let me run it again, because these are random numbers, so who knows? Maybe if we run it again, it'll be fine. Perhaps it can expand from existing dot, but lower chance. Yeah. So I'm gonna say that I'm just gonna put a big to do at the top of this. Okay, well, let's actually do this again, but let's not allow for translation, okay? So while this is running, let's go ahead and edit the code a bit so that this does not allow for translation. So it'll be 0 here and also 0 here. So now it only allows for rotation and scaling, but not translation. See what happens. I don't know. All right, give this a second to run. And again, guys, I do ask if you guys have, questions or anything like that, just to pop them in chat. I'll do what I can to answer them. Yeah, so that still didn't. Yeah, we do see like points up here. Okay. I'm gonna try it again without the translation element. So the idea here was every time before we applied our function, we also maybe did a random translation or something like that. Which probably caused it to go off of the map, right? Because we only have like a camera that's so big, so it doesn't really take a good image of the system. But my guess is that we don't really have to worry too much about this. I think I need to figure out exactly what's meant by the affine transformation, right? That's what I need to figure out. Would love to see a stream about noise generation, how to perform it fast, and how to have control over noise characteristics flow. Oh, like Perlin noise and stuff like that. So I think Coding Train did a video about this not too long ago. Coding Train, Perlin noise. Yeah, maybe this is what he had. But yeah, he's got some really cool stuff here. I mean, here, I'm just gonna put this down here. My man, you're always showing us how to cook up fractal fires, but how do we whip up a hot home cooked meal? Okay, I mean, I cook meals all the time, so I'm happy to do a cooking stream. Yeah, so this just ain't working. Like, well, actually, that's not nearly as bad as it could be. That's reasonably cool. If I had a few more points, that would be pretty nifty. Okay, guys, I'm going to let this run 10 times as long as it did last time. I have no idea how long this is going to take. It might take 5 minutes. I'm so sorry about that. Let's just chat for 5 minutes while we're just chilling. The Thanks for the link. As far as cooking like a home cooked meal, I do a lot of home cooking. I guess maybe because I'm vegetarian, I do a lot of home cooking. Mainly like, beans and stuff like that. I make some really good hummus. Let's see, tacos, amazing. Let's see, I don't know. I just cook my own food. Like a lot of, I mean, fried rice is obviously easy, but like I've been thinking about doing some cooking on stream. Like I have been thinking about it a lot. I was thinking about doing a, how do I put this? I was thinking about doing um, an April Fool's Day video on YouTube where I was just like Bean Boy 012 or something like that. I just showed you how to make beans. The reason this is kind of funny is because to make refried beans, a lot of the time you're going to use a food processor. So it's just going to be like insanely annoying as far as videos are concerned. Like I could imagine just like speaking into the camera and being like, today I'm going to show you how to make beans, and then start the food processor. And then it's super loud so you can't hear anything. And I'll just like keep talking through the food processor as if nothing was going on. I could imagine a pretty funny video like that. A growing dot that spreads randomly, like when you look at vortices in edit mode in Blender. Vertices, and yeah, I don't know how to do that exactly. You might not be able to. It's a galaxy. I don't know, it's a bad explanation. Yeah, it looks like a galaxy. This man just made space. When you bring yourself to streaming, why you decide to make streaming among MIT science work? Fried cucumber recipe. That actually sounds amazing. Right, so the reason I do streaming and I do YouTube and stuff is because the MIT work is kind of not exactly, it's fine. Like my job at MIT is great. But I cannot creatively express myself through the work that I'm doing at MIT. And it feels not as meaningful as, my YouTube videos and stuff like that. The algorithm archive is clearly the most meaningful thing I am doing right now. And to put that on the back burner for essentially software engineering work that I'm doing at MIT doesn't seem really fair, Let's see. Fried cucumber recipe. Maybe a repetitive question. Julia over Rust as a language choice. Thanks. I just don't use Rust. I like Julia. The question is Julia over Julia's competitors, and Julia's competitors are C, Fortran, and MATLAB. Julia over MATLAB is an easy choice for me because I genuinely hate MATLAB with a burning fiery passion. Julia over C and Fortran, though, is a bit different, right? Fortran is genuinely a good language. I love Fortran. It's great. It's just old, right? And for the most part, if you're going to be using Julia, you're probably in the same space as people who are using Fortran. So essentially, it just gives you way more modern tooling than Fortran. Now, Julia against C and C++ is a hard decision, right? The reason being that C and C++ is genuinely, it's faster than Julia, but not by too much. Julia's a factor of 2 slower, but that's not really too bad because it saves you a factor of 2 development time, right? So in my mind, Julia is just way easier to write code for, and at the very least, it's good prototyping. Even so, we have some very big high-performance computing applications written in Julia, and they perform pretty dang well. So let's see. If you have someone to discuss problems and/or expansion of different subjects, that's what makes me want to work with something more. Right. It's not fun if you're alone. Well, the truth is, I'm not alone at MIT either. Like, don't think that I'm alone there. It's just that the project is very physics focused at MIT, and that's perfectly fine. It's just that I tend to get very burnt out when dealing with physics, right? And so, like during my PhD, I was able to get around it because I had a lot of really cool GPU computing to do. And at MIT, I find that it's particularly focused on ocean dynamics, specifically at MIT, right? So I tend to get kind of a bit bogged down when people start talking so much about oceans. So I need like just a reprieve, a little bit of time every day where I focus on stuff that I find enjoyable. And for me, that's streaming. It's talking about algorithms and methods and stuff like that, which is of course dramatically different. Different people think different things. But for me, I personally need a little bit of time for writing, a little bit of time for, working on the algorithm archive, stuff that I find enjoyable, right? And don't get me wrong, job's still enjoyable. It's just, it burns me out really quick. So I need to find something to expand beyond that. Okay, so that's my answer. I guess I maybe should have put the Rambaleo stream up while I was doing that, or the Rambaleo screen up. I hope you're developing a way to communicate with whales at MIT. What are whales? I don't know what whales are. Sadly, my brain and thoughts are blank because of my anxiety medicine, so I have a really hard time focusing. I have a huge amount of anxiety, and also like really hard for me to focus as well. I know how that goes, you know. Would have loved to learn a lot more. Actual whales, porpoises, etc. No, I didn't. I guess maybe there whales around MIT about code. I genuinely like programming. It's something that I think a lot of people here also probably like. Okay. So while we're waiting for this code to run, I think I'm just going to start talking a little bit about symmetry. So let's just open up this paper, and let's just see what this outputs in terms of a flame. If it looks cool, we'll keep the affine transformations. If it doesn't look cool, we'll get rid of them. And let's just start talking about the variations here. Because it does feel to me like, it really does feel to me like this looks like they did some sort of affine transformation beforehand. And this one feels like they didn't. I mean, with your ocean research. Oh, right. Yeah, I forgot. I do stuff with oceans. No, I do mainly high performance computing work. So that is to say, even though I do oceans, I do ocean simulations. So that's kind of what I focus on. Have you studied quantum computer development? Seem plausible to have a million qubits work in nature? A million qubits seem incredibly large. So, but let's talk about why, right? So my PhD was in quantum simulations, not quantum information. So I didn't do too much with qubits. But I will say that the reason a million qubits is insanely large is because there's a difference between a quantum computer that can talk to its neighboring qubits and a quantum computer that has an n-connected network. By the way, I don't know if I said thanks for following Mudbound Dragon, but thank you so much for following a few minutes ago. So like, okay, let's talk about a quantum computer real quick. Just real quick. Okay, so let's go here. I'm gonna erase this because I don't even know what I was there for. I mean, I do, but you know. So let's say you have a qubit, right? There's a lot of things you need to consider when talking about qubits, right? Like they've got an upstate and a downstate, right? And that is to say, you know, downstate here, 0.5. If you were to measure a qubit, you know, you could say that it has some probability of being a positive state, some probability of being a negative state. And there's some interesting, you know, things to deal with. Entanglement, how one bit can be entangled to another qubit, right? Now here's the problem. If you do 3 qubits, all of these qubits need to be connected, right? If you do 4 qubits, they need to be connected still. To be we'll call it a real quantum computer. Now hear me out. This isn't exactly how it's done in practice. But in principle, if you want a true quantum computer, all of the qubits must be connected to all of them. So if you have a million qubits in a network, every single one of the million qubits must be able to interact with any one of the other qubits at any given point in time. So what people do in practice, instead of actually doing a million qubits together like this, is they do this thing where they do kind of a nearest neighbor thing. So they only say that these 3 qubits are connected to each other, or they're connected to each other in this way, right? So here, these guys are connected. But for example, these guys are not connected, and these guys are not connected. So if you want a true million qubit connected quantum computer, that's going to be kind of hard. But if you want an approximation to the million qubit device, in principle, that could be done with quantum circuits like you have in D-Wave or something like that. And there's a lot of people doing that, right? So that's kind of cool. Whoop Tenchi and also Bike Much, thank you guys so much for following. Really appreciate it. Let me catch up here. I mean, wow, those are gorgeous. Thanks. My pleasure. Fractal Flames. These digital pixel works in Julia remind me of these artworks. Yeah, let's take a look. Also, for the record, Sabrada, you might have already known this. I do apologize for maybe potentially going on a rant, you know, on stuff that you already knew. But I think it's important for people who aren't in the know. I agree. Any connected network seems won't get meaningful results. I doubt nature can comply with such a massive entanglement. Oh, this is an interesting. Yeah, that looks interesting. Nice. Thanks for sending that. Okay. I guess the only other thing I want to point out while we're still waiting on this code to finish is that as far as quantum computers are concerned, there's actually a number of different ways in order to generate quantum computers. You have obviously the quantum circuits and stuff, which I think use mainly Josephson junctions, but I'm not entirely sure. I need to kind of look into that. But you also have like cold atoms and ions, and you know, you could also use photons and a whole bunch of other things, right? So there's a huge number of ways in which you can generate like quantum entanglement and stuff like that. And basically, in any system that you can generate quantum entanglement, you can generate a quantum computer. I say that, but I say that with conviction. But if someone told me I was wrong about that, I would not. I could potentially be wrong about that. But essentially, you just need to be able to write the states in a particular way. And as long as you can write the quantum states in a particular way, like I did over here, with some sort of probability of being in one state or the other, then you have a qubit, right? A lot of people are actually looking into Q-trits, which are 3-based, qubit systems, and Q-dits, which are 4-based quantum systems. But, at some point, you just got to say, trits and dits weren't particularly useful for regular computing, so they're probably not going to be too useful for quantum computing. As you zoom out, will the communication become slower, or am I misunderstanding? Let me see. I don't know. You're talking about this diagram in here. Okay, so the truth is, if they're properly entangled, the communication between okay, let's talk a little bit about entanglement, just to make sure we're on the same page here. If you have a qubit system, right? So let's say we have a qubit here and a qubit here, and they're what we call entangled. That is to say, if this guy is an upstate, this guy is a downstate. And if this guy is a downstate, this guy is an upstate. If you measure one of them, let's say we measure this one, then this guy over here must be the other state. So for example, if we measure this guy to be in the upstate, then this guy must be in the downstate because they're entangled, right? And this entanglement means that their states, their inner states, are related to each other. Now, when you say if you zoom out, communication becomes slower, you are right that communication does become slower. However, the communication between qubits is the same speed because this interaction, where this measurement interaction happens instantaneously. If you are to say that, this qubit's in the upstate, the other one must be in the downstate, and that happens instantaneously. However, you can only transmit this information at fastest the speed of light. C is equal to 3.0 times 10 to the 8th meters per second. And so the only way you can use that information that the other state is in the downstate is by transmitting that information via a classical process, and that classical process would be light or something like that. So as you zoom out, the communication time does increase, but it's not because the qubits take longer to communicate. It's because the system is just bigger and it takes longer to send that information around. Let's see. Josephson junctions, like circuits, only exist at absolute zero. That's true. Yeah. Atom versus photon. The questions between atoms and photons, I don't know if I necessarily want to go into that right now. When you're doing atoms, you're entangling two inner states usually. And if you're doing photons, it's usually more directly like photon interactions. Do you have a link to the paper you're working off of? Yes, I do. Let me go ahead and go over here and let's just paste that there. This is something I can research myself, no problem. Yeah, please do. And feel free to talk about this kind of stuff on chat as well. I do appreciate these conversations. Even if they are a bit off topic, I think that's okay. I don't mind being off topic. Let me get another quick sip of water. This is still taking time to run, so we're just going to go through this paper and I'm just going to look at this whenever it's done. In fact, let me go ahead and run HTOP here. I'm using 12 gigabytes. Oh no. That's a lot of memory, but that's okay. Okay. So we're just going to read through this again and yeah, hopefully it's interesting. So the next thing we're going to talk about is symmetry. So if you look at this image here, you'll note that it's not symmetric. This area up here and this area over here, they're not mirror images of each other. And if you looked at the last image that we generated, which I will show here, and we zoom in a little bit, you'll note that is really not symmetric, right? Like, it's just not. So, let me make it bigger so you guys can maybe see it a little bit better. Oh, sorry, I screwed up. So this is really not symmetric. So if we're gonna do some form of manipulation to this image, we're gonna have to do some things to make it just look prettier. And one of those things is by, making the eye appreciate it more, and human eyes appreciate symmetry. So that's what we're doing next. We're gonna talk a little bit about symmetry and how to make these images even prettier. So The first thing here is the human mind responds to symmetric designs at a fundamental level. When the matrix coefficients are chosen at random, the chances of a symmetric design appearing are vanishingly small. We can easily inject such functions intentionally, however, the results appear in figure 5. So this is where I started asking myself and why we went back to apply the affine transformations, because this thing, when matrix coefficients are chosen at random, it was kind of weird that they said that, so I didn't fully understand why it was said, and so now we're just testing that over here. That's what's running on the side. The housist Rick, thank you so much for following, really appreciate it. Without being too personal, is your PhD work fascinating in public domain or other published quantum research? Yeah, it's available. But again, it's not what you think. So if you go to James Schlaw's Google Scholar, all of my papers are available open access, so you can read them. They are not public domain, but they are open access, so you can read them all. Are they great papers? They're okay. Like, I'm not going to pretend that my PhD work was like revolutionary and, you know, changed the landscape of human knowledge as we know it. It was a PhD. It was okay. The actual thesis was massively parallel split-step Fourier techniques for simulating quantum systems on graphics processing units, and I published 4 papers in the work. I published 1 paper on chaotic few body vortex dynamics in rotating Bose-Einstein condensates, controlled creation of 3-dimensional vortex structures in Bose-Einstein condensates using artificial magnetic fields, my code base that I used, GPU-E, and then non-adiabatic generation of Newton states and tungstar audio gases. So this was kind of what I spent all my time doing. Mainly writing GPU code to do simulations. And yeah, I think it was cool. I think it turned out okay. Cool, so the image is now done. Let's see what it looks like. We're on check.png. Okay, so this is kind of looking better, right? Like, this says to me that maybe doing that affine transformation is what we wanted to do, because this looks quite cool. Admittedly, though, it's a far cry. Like, I really do think that this visualization here is way cooler, right? Like, this one just looks cooler. So what I might do is I might just remove the affine transformation for testing, and we'll put it back later. So we're going to go here to source transformations. Oh, sorry. VI source and then fractal flame.jl. And I'm going to add an optional argument here, which is just going to be a Boolean, which basically says do affine equals false. And basically you're going to have to turn this on manually for this particular function for now. So here we're just going to say if do affine. Sure. And perfect. Oh no, it's okay. I'm just gonna move this down to the next line. All right, perfect. Similar to above, I'm just gonna yank this and paste it here, there, and also there. Okay. And then end in here, and then another end in here. We're gonna get the spacing in just a second. Sorry about that. And just, I know it looks ugly, just, you know, 1 second. And in here, we're going to do that. Add some spacing in here and in there. And then finish this up here. I'm sorry, this is such a weird way to do this. I do apologize for that. And all right, this should do it, I believe. So if do affine, if do affine, if do affine. So this should generate the image that we had before, essentially. So let's run this again with way fewer points than we did that last time and just see what it outputs. And then this should look similar to this image we have in the upper left. It does look similar. It's a low quality, low resolution image, but it looks similar. I'm happy with that. Okay, because again, the identity matrix is an affine transformation, so it's totally fine. Why do you not use syntax highlighting? LimeDie, I'm pretty sure you've asked that question before. Did you see the Dev series 8 episodes on Hulu dealt with fictional quantum computer? Oh, I have not. But yeah, the reason I don't use syntax highlighting is just because it bothers me. Like, that's it. There's no other reason. I just don't like my code with syntax highlighting. I think it looks ugly and it's hard to read. So that's why I don't use colors. That's it. That's the only reason. I like to think that I space my code out and stuff like that, so you don't have to rely on the syntax highlighting. to make it readable. But, you know, readability is one of those things that kind of comes and goes. Some people can write really readable code, you know, other people can't. And, you know, I'm kind of somewhere on the line of people who can and can't. Also, before going any further, because I know I'm going to forget, let me just go ahead and commit what we have here. Get status, get add, I think I just get add dot, get status again, get status, sorry about that, get commit, -m, and we're going to say adding the ability to, what did we even do today? One second, we did a lot of stuff and I don't remember any of it. Wayne249, thank you so much for following, really appreciate it. Major Lizzie, man, I need colors to be able to read code. Yeah, I'm sorry. I know a lot of people in chat say that. But you know, I've been streaming for years, and look, I could use colors. It's just that you become quickly reliant on them, you know. And I don't. Here, I'll explain it in just a second. I think I have a good way to explain this. Adding the ability to do affine transformations. Actually, adding the ability to specify colors and affine transforms for each function. All right, git push origin development. All right, great. Okay, it seems like some people's brains react better to it than others. Yeah, that's true, right? I use colors as a distraction from the crushing pressure of actually having to write code. Oh no. But let me just open this up in Vim. So we're going to open up Vim source and then fractal flame.jl. Okay, so here's what happens to me when I'm trying to read code with color in it, right? When I'm trying to read code with color in it, my eyes naturally skip colored things, right? So white is to me the most important color, right? Because it's the direct opposite of black. Right? And so for me, my eyes naturally go to all the white bits first. The next bit they go to would be all of the yellow bits, you know, like this to-do statement, this function. The next thing they go to would be all the pink bits here. And then finally they go to the blue bits here. That's just how my eyes work, right? The issue with that is that I find that I'm actually genuinely blind to certain colors. As I'm trying to read the code here, I personally, it took me like an extra second to realize this line even existed. And so for me, because I'm so used to dealing with code without colors, when I have code with colors, my eyes just skip everything that's colored and I only look at white things, you know? It's like the Julia error messages. Like the error messages are probably fine, but because the error messages are in big, bright red and they're bold, I don't see them. Like it literally says, look here. And because I'm so accustomed to not looking at colors, I don't see it. It's the same thing with advertising, right? Like your eyes don't look at the ad. Even if the ad is the most flashy thing on the screen, your eyes don't look at it because you know not to look at the ads, right? And so that's the same with me encoding with colors. I end up just not looking at any of the colors, and it ends up being really frustrating because I'll spend like even a minute or two trying to figure out what's going on with my code, only to realize it's commented away or something like that because I didn't genuinely see the comment, you know? So this is my personal struggle with using colors in code. It just, to me, I feel like every line, every character in your code should be equally important. Now, I will say that when you're commenting out big blocks of code, sometimes it's useful if you're commenting out like a block here and a block here and a block there. Sometimes it's useful to have colors, and I do open up Vim in these cases. But for the most part, I haven't really needed to open up VI or anything but VI in a very long time. We didn't evolve the code as such. It's no real surprise that some people's visual cortex needs completely different stimulation than others. Yeah, that's true. By the way, nice name for that comment. Exactly, my eyes jump around the screen and I miss parts. Spend 3 hours to set up environments perfectly with proper syntax highlighting. Spend an hour to actually write code. I use shading, but not colors. Yeah, I think shading would work as well, but I'm happy with my setup. Even if everyone else hates it, it's fine. Like, who cares? Like, it's my setup. And the way I see it is, you know, if you have a different setup, if you love using Visual Studio, if you love using, I don't know, if you write your code in Microsoft Office, you know, just you open up a Word document and you just write your code in there and then you copy it into, I don't know, like a Python shell, and that's how you do coding. I might judge you a little bit. Like, I would definitely judge you a lot, actually. But like, if you're efficient, who am I to, like, I know I'm in the wrong for judging, you know, like, you shouldn't, who cares? Like, it genuinely doesn't matter what you're writing code in, as long as you're happy writing code in that way, right? Like this is how I feel about IDEs as well, right? Like I know I should definitely put up the screen now. We're completely off topic. But when it comes to IDEs, I feel the same way. I feel like, I just don't like coding in IDEs. I don't like coding in notebooks. And for that reason, when I'm coding in notebooks, my enjoyment of programming drops way, way down. LaTeX is the same way. I personally know LaTeX is way less efficient than using Microsoft Word for most things. But I still use LaTeX because I like it. It makes the process of writing reports fun. And that's the thing. If coding, if your IDE, your text editor makes coding boring, then you're using the wrong text editor. Anyway, done with the ramble session. Let's get back to reading about fractal flames and symmetry and stuff. I actually saw someone coding in Word. I'm sure it happens. I did that when I was in junior high and I was learning to code for the first time. I didn't know what a text editor was, so I wrote code in OpenOffice at the time, and I just pasted it into my terminal because that was the only thing I knew how to do. Because honestly, I think the hardest part of learning to code is that first step of setting up your programming environment and trying to figure out how to run code for the first time. Once you have it running, I think the rest of it actually comes much easier, It might be because you have forward momentum. It might be because you know how to code now. But I do feel like there's that element of learning how to initially compile code that people just don't recognize how hard that is. And I think it's genuinely one of the hardest steps to programming, that first step. Okay, let's just keep going. LaTeX is not less efficient than Word. Everyone says that. Has not had the problem that he wanted to place a pic somewhere else and messed up the entire ordering of the document. I agree with you there. It's just I read a study recently saying that it was about people who were it was about academics who were writing reports in both LaTeX and Word, and they found that people who wrote their reports in Word genuinely got the reports done way faster, but the people who wrote in LaTeX were way happier writing the reports. The environment config is a huge hurdle for me developing. Yeah, I'm 100% with you. It's, to me, the hardest part of programming is that first step of setting everything up. Everything from there, understanding programming. Like when I was reading my first C++ textbook, right? Again, I was 14 at the time, so what did I know? But as I was reading through the textbook, I genuinely had no problems whatsoever understanding programming logic. I could read the code. I understood what it was trying to do. No issues with that. Recursion, easy. What I couldn't figure out how to do was freaking run the thing. It wasn't until I learned that you could compile it in your terminal with GCC or G++ that I was able to actually write code. And just that moment of being able to just run G++ file.cpp, that was a moment I was like, that I finally understood, And it took me literally 2-3 days to figure out how to run that code. But then once I ran the code, I could run 5 different problems at the same time because I already had them all ready to go. I just had to figure out that one step, So I guess if people here are trying to learn to program or something like that, know that no matter how good you are at programming, there's always going to be an element that first step's always going to be difficult, I think. So yeah, environmental config. Okay, so let's keep going. So I'm going to start reading again. Let's just start here. So there are two kinds of symmetries, rotational and dihedral. First, we cover rotations. Adding a function to the system that rotates by 180 degrees makes a two-way rotational symmetry appear. The weight of this function should be equal to the sum of the weights of all other functions in the system. Okay, so the idea here is that they just do an additional rotation. Okay. So here, I think what I'm reading is that they do a 180 rotation, which is great because we already have a rotation function, right? So we can just do that 180 rotation. That won't be too hard to do. The weight of this function should be equal to the sum of the weights of all other functions in the system. Now, I'm struggling to understand what they meant by that. That way, half of the jumps in the chaos game are between the two halves. I see. So you have a 50% chance of doing this rotation. If the rotation function is given the same weight as the other functions, then one of the two halves will only be a shadow of the other. Right, okay, fair enough. So you're just saying you have a 50% chance of rotating. Adding a rotation by 120 degrees does make a three-way symmetry appear. The three branches do not have equal densities, however, and no weighting would balance them. That's because in order to get into the 240-degree branch in the chaos game, one has to pick the rotational function twice in a row, which is only 25% probable. But the 120-degree branch is 50% probable. Instead, one must introduce two transforms, one by 120 degree and another by 240, and give them both weight equal to the sum of the others. Then all three branches will have the same probability. In general, to produce an n-way symmetry, n-1 additional transforms are necessary to balance these densities. Okay, that's fair. So basically they're saying if you want a symmetric image, you rotate by 180 degrees. So you basically flip the image. If you want three-way symmetry, you have to rotate by some number, right? So, yeah, that's fair. Yeah, I bought a ray tracing book using C++ years ago, using Microsoft's version of C++ code examples. Simply wouldn't, using Microsoft's versions of C++ code examples simply wouldn't compile. Yeah, I've had that experience so many times. Like, don't get me wrong, like, learning to code is genuinely enjoyable. I found the process of learning to code to be quite fun. But that doesn't mean that everyone else did. And the reason I found it fun was because it was a constant tinkering, a constant trying to figure things out. That honestly, the book probably should have taught you. And so I can imagine why it's frustrating for a lot of people and why a lot of people quit. Okay, so a dihedral symmetry is created by adding a function that inverts the x-coordinate only, producing bilateral symmetry. Again, it's given weight equal to the sum of all the other weights combined. Combining this function with the rotation function gives all the dihedral symmetries. Dihedral symmetries are named with negative integers, so the simple bilateral symmetry is -1, and snowflake symmetry is -6. Combining this function with rotation. Oh, I see what they're saying here. Okay, I understand. Okay, so here's what you got. Journal, new page before. You've got a bunch of different symmetries. So the first symmetry is going to be taking your image. Let's say your image looks like this arrow in here, and rotating it 180 degrees. So it'll look like this. So that's the first symmetry they talked about. Now, the next symmetry they talked about was one that is going in n, like kind of n directions. So you have one that goes like this, and then another that goes like this, and another that goes like this, right? Finally, you have a symmetry that allows you for flipping. So for example, if you have an arrow that goes like this, it'll actually flip you to look like this. And if you combine the two of them, then you can get images that, oh, I need to think about this. How did they say it? So combining this function with rotation gives all the dihedral symmetries. Dihedral symmetries are named with negative numbers, so the simple bilateral symmetry is -1. So let's see if I can figure this one out. So here's examples of symmetry. Image D shows that the colors wash out without special treatment of the color coordinate for the symmetry transforms. Okay, so I think what we have to do here is implement a new symmetry operation that does either rotation or flipping along an axis. It's also possible to introduce symmetries by modifying the chaos game to support them directly instead of adding symmetric functions. For example, one can just add an integer symmetry parameter, and then after picking a function at random, pick a rotation at random. But then how to interpolate between symmetries without discontinuities is problematic. Okay. Getting good colors with symmetry functions, come on, requires special treatment. The problem is symmetry functions can bring a point back onto itself after 2 or more applications. If the color is modified by these functions, then plotted as its original locations, different colors get averaged and the image loses color diversity. The solution is to not change the color coordinate when applying symmetry functions. This also makes the color symmetric as well as the shape. Okay. So this made me rethink everything that we just did with the code that we just had. So first of all, they're talking about color coordinates. Okay? That is not what we did. We didn't do a color coordinate. We have a separate color associated with each function. So that each function will color, so like for example, the swirl function will color it blue, or the, heart function will color it pink, or something like that. That is significantly different than how they're speaking about it now. So it makes me wonder if we are implementing things wrong and we have to go back and think about that. Let me see what they have for filtering really quick. And maybe, okay. I know they have motion blur. Okay, so they also have this idea of like moving parts. You know what we're going to do today, guys? We're going to read through the rest of this paper today. We might not do any more actual coding. We might just do more theory, trying to understand what it is that they're doing. And then we go from there. But, I said we're not going to do any programming, but I am going to, you know, write some stuff down for what we need to do tomorrow. So we're going to do transformations. Ooh, let's try that one again. VI. And in here we're going to say like to do. And in here we're just going to say, you know, we've got to implement a symmetry function that does the following. Okay, so let's see, how am I going to do this? So 1, it allows for rotational symmetries. And then 2, what did they call it? It wasn't rotational symmetries. It was they called it dihedral symmetries. Inversion symmetries. Long axes. Okay, so with that together, let's think about how we are going to write this function. Again, we might not do the writing today, but because I don't have too much longer in stream today. But we will at least kind of think about how we're going to write this. So this function here, so just as a thought, let's do function apply symmetry. Okay. So I guess what we want is the number of axes, rotational axes, and which axis we're going to be flipping over. So I guess we want number. I think I'm going to do it this way. So they're all optional arguments, and we're going to say rotational number equals 0. And then we're going to say axis, flip axis, I guess is what I'm going to call it, is going to be equal to, I'm just going to say 0 as well for now. And we'll say 0 is going to be like no axis or something like that. Okay, so this is how I'm kind of conceptualizing the function, and we're going to come back to write that later. And I'm going to do that for a few other things as well. So let's get through this filtering bit. And then we're going to, yeah, let's just go through the whole paper. Oh, well, maybe not the whole paper. They also have, oh no, we can do the whole thing. It's not too much longer. So sorry guys, we're going through a paper today. It is what it is. Like this is how it goes sometimes. Again, guys, if you have any comments, questions, concerns, ideas, anything like that, just let me know, and I'll totally address it as if I see it in chat. The other thing to point out here is that we do have a Discord. Feel free to go there if you have questions or anything that we can't get to on stream. Again, I don't really have too much longer, maybe another anywhere between 10 and 30 minutes. But yeah, I will be ending soon. So if there's somebody that you want to raid at the end of stream, let me know that as well. Okay, so filtering. Aliasing in spatial and temporal directions is visually disturbing and also indicates information loss because one cannot tell if an artifact in the image is original or an alias. Fair enough. With anti-aliasing, there is no ambiguity. The chaos game lends itself to anti-aliasing. Consider spatial aliasing first. That is the elimination of jaggy edges. The normal technique is to draw the desired image at high resolution and then filter it down to display resolution. This is known as supersampling, and its cost is linear in time and memory. So they want us to do supersampling as well? Like this is already taking forever to generate like these images. So if we do supersampling, we're gonna have to find a way to parallelize this. Cool stuff, not academic, but knows. Yeah, right. I think I'm following him as well. This is known as supersampling, though the sampling is normally applied in 2 dimensions, so 3x3 supersampling means 9x. With the chaos game, however, we can achieve this effect by just increasing the number of buckets used in the histogram without increasing the number of iterations. There is a small sublinear cost in time, though, because the time spent filtering is significant, and the increased memory usage also means increased cache misses during iteration. The effect on visual quality, however, is dramatic. Gamma correction should be done at this filtering step when the maximum number of bits of precision is still available. Okay, so let's go here and let's go into VI source fractal flame.jl. I believe we've already done these 2 to-dos, which is great. So let's create some more to-dos. Okay, so the next thing we want to say here is super sampling must be implemented by increasing the number of bins before sampling down. gamma correction at that stage. Come on. Perfect. Okay. How are you generating these images? There are several GPU fractal flame implementations that are near real time. I don't know how you do a massively parallel. How do you do massively parallel iterated function system? It's by definition not parallelizable. Right? I mean, the chaos game is iterative. Iterative function systems are just giant trees that you recurse through. So they're not particularly good for GPUs, right? If you have a bunch of IFS with different starting seeds, right? That's what I was thinking as well. That's not particularly good for the GPU, but it's fine, I think, because the calculations are relatively quick. So yeah, we should do that. In fact, we'll probably deal with parallelization next. So to do parallelize with large number of initial points, and that should do okay. Okay, so we'll do that probably not tomorrow's stream, but maybe the stream after that. So right now I'm just using pure CPU, but turning this to GPU code should be relatively quick, especially because it's all computation at this point. I was not going to be using OpenGL. I was just going to be using the inbuilt Julia libraries. In fact, maybe this is a good opportunity to use kernel abstractions, which allows for you to do GPU and CPU code at the same time. It's just you write one function and it heterogeneously computes, which is actually pretty cool. So yeah, we'll see how that goes. Despite this filtering, the logarithm and gamma factors may cause low density parts of an image to appear dotty or noisy. A wider filter would solve this, but at the expense of making a well-sampled image, making the well-sampled parts of the image blurry. This can be addressed with the form of density estimation. We have implemented a dynamic filter where a blur kernel of width inversely proportional to the density of the points in the histogram is applied to the samples. The blur kernel is scaled based on the supersampling level. Oh boy, and is applied after the log density scaling. This variable width filter allows higher density areas to remain in focus, while lower density areas are significantly smooth. Figure 6 illustrates the effect of density estimation. That one's going to be fun. All right, step 2. Sure. Ah, dang it. This will be 2. Okay, density estimation with dynamic kernel of size of related to of the number of points in the bin. Lower points equals broader kernel. More blurring. So that should be, that's going to be interesting. We're going to have to implement our own convolution. That's totally fine. I was very much expecting to go into convolutions a bit. So I think the way that we're going to do this is go through super sampling, parallelization, and then we're going to take a step back and talk about convolutions at that point. So that's pretty good. I'm actually kind of looking forward to that. Okay. The variable width filter allows higher density areas to remain in focus. Yeah, that seems fine. Okay, so finally, motion blur. Motion blur, or temporal anti-aliasing, is not so easy to do correctly. Supersampling can be achieved by varying the parameters over time while running the chaos game. That is, if 5 million samples are used to draw the frame at time t, to instead use 1 million samples at time t minus 0.5, 1 million samples at t minus 0.25, 1 million at t. Oh no. T plus 0.25 and 1 million at t plus 0.5, all while accumulating into the same buffer. That would be 5 times super sampling for free. With a linear density display, this would work exactly. The non-linearity of the logarithm complicates things. Consider a pixel with density 8. Assume for simplicity the logarithm is base 2, so its assigned brightness is 3. Now put the fractal in motion so it blurs across 2 pixels. Each should get brightness 1.5. But if the motion takes place before the logarithm, then the 8 samples would be divided into 2 pixels of density 4 each, whose logarithm is 2, not 1.5. Objects in motion would appear unnaturally bright. Okay. I kind of get what they're saying here, but here's what I don't understand. What is changing with time exactly? So I'm assuming then this goes back to the affine transformations. So the idea is that like you have like a transformation for one function and another transformation for another function, and they're slowly transitioning from one to the next. And so, you know, you have that time variable changing. So your affine functions will change with time. Here's a paper of techniques for vectorizing fractal flame algorithm. Yeah, post a link. I'd appreciate that. So down here, we're going to say another to do. Again, we're just kind of figuring out what we need to get done. So the next thing we need to do here, allow affine transforms to have a time variable, and allow for super sampling across time with different time steps. Time steps all falling into the same bin. That should do. Okay, yeah, let's take a look there. Okay. High performance iterated function systems. Oh, great. Yeah, actually, we should probably go through this then. Yeah, we should almost certainly go through this. This will be interesting. I appreciate that. Thanks. I'm actually going to star this so I remember that to look at it later. Okay. So this is great. Yeah, thanks for that. I really appreciate it. Let's see. A proper solution requires the use of an extra buffer. The first buffer is linear and accumulates the histogram. After each temporal sample, take a logarithm of this buffer and accumulate it into a second one, applying the density estimation filter in the process. After all samples are completed, the second buffer is filtered down into the final image. Okay, I see what's happening here. Requires two buffers, one for log of each step, another for all logs. All right, great. We're getting there, one step at a time. Takes time, guys. Perfect. Okay, so after experiments with single buffer yielded acceptable results, we decided to default to single buffer renders while retaining the options of using extra buffer. Okay, so they said might require. Oh no. All right, here, there, perfect. Okay, so the last thing we have is directional motion blur. So uniformly distributing the samples among time steps works well for an animated series of frames, but the illusion of motion of an individual frame animation may be improved by providing a sense of direction. Early attempts, sorry, I can't read, at directional motion varied the number of samples used at each time step, but since the density estimation filter was more aggressive during less dense time steps, the result appeared unnatural. Instead, the color of points accumulated during earlier time steps are scaled in intensity, with the scaling constant approaching 1.0 as the time step progresses. A render parameter can be supplied to the renderer to change how aggressive the blending varies throughout the time steps. See the effects of directional motion blur in Figure 7. Okay, so what are they doing here? The color of points accumulated during earlier time steps are scaled in intensity, with the scaling constant approaching 1.0 as the time steps progress. Okay, so I guess what they're saying here is they count how many points fall in a bin in time step 1. Then they count how many points fall in the bin in time step 2, and they create some sort of motion vector, and then they blur in that direction of the motion vector. I don't know if I said thanks for following Zemero89, but thank you so much for following. Really appreciate it. Okay, I think the directional motion blur, I'm going to say, is going to be that's going to be an addendum. Like, it might not be, I'm just going to put a to-do statement to think about this. Because they didn't really provide enough information in the paper to really, like, figure that part out. Okay, so that sounds like a pain in the arse, to be honest. If you're paralyzing, you might as well do each IFS at a different time slice. Yeah, so there's some bits there with parallelization that I'm confused about, right? So that's why I'm interested to read the paper that you sent. I think it's actually going to be quite useful. So what I'm going to do is probably we're going to go through and just get everything implemented on a single core. Then we're going to talk about parallelization, talk about convolutions, talk about ways to parallelize convolutions, probably via FFTs. Maybe, I don't know, because the filter changes in size, we're probably going to have to roll our own convolution, which is not great because convolution is done iteratively on the GPU is kind of a nightmare. Fine, fair enough, we'll do it. You know, like if it needs to be massively parallel for speed, we'll do it. Like I know GPUs, it's what I do. So it's not particularly uncommon for me to do this type of stuff. The problem here is we want this runtime to be as fast as possible because the reason I'm creating this function at all, or this package at all, is because I actually want to take it one step further. After we get Fractal Flame perfectly implemented, right? Then we have basically a parameter space to sweep through, an n-dimensional parameter space where n is whatever you want it to be, with a huge number of functions to sweep through and a huge number of different variations we can play with. What I want to do is I want to put an image in the background and have a cost function associated with that image. So we basically sweep through the entire parameter space, you know, this 100-dimensional parameter space of our fractal flames. And we try to make a flame that is as close as possible to the image. And I really want to try it. I want to try it so badly because I just want to see what we could do. So that's where I wanted to go with it. So I'm not so worried about things like directional motion blur or motion blur at all, because that's, you know, time. I don't really care that much about that, but I do care a lot about getting good still images. And having some motion blur on top of that would also be really cool, but I'm not too worried about that step. Like that's a step in the far future. Like, again, we'll think about that when we get there. But I think this right now is a good place to stop. Again, I see where we're going. I think we've made some really good progress today. I'm quite tired, so I'm going to go ahead and leave for now. You guys said you wanted me to raid Gamozo, so I'll go ahead and start that raid on Gamozo, who is definitely live, and they are doing Android exploit we wrote to dump a phone and something. Okay, so let's go start that raid. Raid Gamozo. And that is it for today, guys. Thank you so much for coming in. Have a wonderful day, night, afternoon, morning, evening, whatever time it happens to be your time. Again, join us on Discord. Batuleos just dropped a link. And yeah, I'll see you around next time. Bye, guys.